will present a theory and implementation of a system supporting runtime verification of past-time first-order temporal logic with time constraints. The general problem is that of checking an execution trace against a formal specification to verify the correctness of the trace. The talk is organized as follows. First, we briefly introduce the term runtime verification. We then introduce propositional temporal logic for runtime verification, where we only can observe Boolean flags in the trace. This logic lays the foundation for the first order case, where events can carry data. We present this case next. As it turns out, BDDs are useful for representing these data. We briefly introduce the concept of BDDs. We then explain how BDDs are used for runtime verification of the first order case. Finally, we extend this logic with time constraints. Let us first put runtime verification into context. One can generalize the problem to that of verifying that some program or system satisfies a formal specification of its intended behavior. We thus have a program and a specification. In general, we can perform runtime verification of any system producing observable events. One approach is static analysis, for example, theorem proving, where we do not execute the code but use its structure to carry out a deductive argument. We can include model checking in this category. The alternative approach is dynamic analysis, where we execute the code. Here we interact with the inputs to the program and the outputs from the program. More specifically, this includes test input generation from specifications, also referred to as model-based testing. And it includes runtime verification, where we focus on monitoring the outputs of the program. Outputs can include events generated specifically to support monitoring. If we compare to model checking, in model checking we check infinite execution traces exhaustively, whereas in runtime verification, we check finite prefixes of an unbounded execution. At any point in time, we have observed a finite trace, but as the execution continues, this trace is expanding, hence the term unbounded. Note that runtime verification techniques can be applied to logs produced by a program. This is also referred to as offline monitoring. For a runtime verification architecture, a property formulated in some formalized logic is translated into a monitor. The system to be monitored is then instrumented to emit events to the monitor. The monitor can emit verdicts or it can provide feedback to the running system that the property has been violated. Work on runtime verification is usually concerned with optimizing one or more of the following dimensions. The monitor has to be efficient, both time-wise and memory-wise, and have as little impact on the running system as possible. The specification logic should be as expressive as possible, permitting the user to express the properties required. And finally, it should be as easy as possible to write and read specifications written in the logic. In this presentation, we shall focus on past-time temporal logics. The algorithms we will present work specifically for this case. We start with propositional temporal logic, since it lays the ground for the BDD-based algorithms for the first-order case. In the propositional case, a trace is a sequence of Boolean propositions. The following two formulas are examples of propositional past-time temporal properties. The first formula states that whenever a close event is observed, then in the past an open event must have occurred. We assume that this property is checked for every new event in the trace. There is an implicit box operator in front of the formula stating that the property must always be true. The second formula expands on the first by demanding that in case a close event is observed, then in the previous state it must hold that there was no close event since an open event occurred in the past and that such an open event did occur. Let's look at the syntax in semantics. A formula in the core form is either constant true, a proposition, the conjunction of two formulas, the negation of a formula, the previous state formula stating that the argument formula holds in the previous state, and the since formula stating that the formula psi, the right argument, must hold in the past, and since then phi, the left argument, must hold. This is reflected in the semantics that we see in the lower left corner. The definitions are standard and define when a trace sigma in a position I satisfies a formula. We explain the last two. The formula previous phi is true if phi is true in the previous state. The semantics of phi since psi is true if there exists a trace position j such that psi is true in that position, and for all later traces k, phi is true. At the bottom, we see the definition of when a finite trace satisfies a formula. A finite trace satisfies a formula if it is true in all positions. To the right, we see a set of derived formulas, the standard Boolean ones and then the last two. Past phi, the letter p, meaning that phi is true sometime in the past. And history phi, the letter h, meaning that phi is always true in the past. Let's now look at the approach for monitoring such propositional past time formulas. We first observe that the semantics of the since operator satisfies the equation shown in the blue box. This equation states that the formula phi since psi is equivalent to the following formula. Either psi holds now or phi holds now, and phi since psi was true in the previous state. As can be seen, we are only concerned about values of formulas in the current state and the previous state. This observation led to the monitoring algorithm presented in the following and described in the shown publication below. Let us look at the evaluation of a very simple formula against a very simple trace. The formula states that close is true now, and in the previous state, open was true. Note that such a formula can change value back and forth between false and true as the trace is processed. In the lower left corner, we see an abstract syntax tree representing the formula. The formula is here broken down into its subformulas. The subformulas are numbered from 0 and up, with the highest numbers lowest in the tree. This is later used in the algorithm. We now observe the first event, which is an open. The subformulas evaluate as shown. The closed formula evaluates to false, this is node 1, and the open formula to true, this is node 3. But the previous open evaluates to false, this is node 2. As a result, the whole formula evaluates to false. We now observe the second close event. We create a new abstract syntax tree of the same shape and evaluate our subformulas in that. The nodes evaluate as shown. Note how the evaluation of node 2, evaluating previous open, looks up the value in the previous tree. The actual implementation uses two arrays, pre and now, indexed by the numbers assigned to the subformulas, for storing the Boolean values of the subformulas. As we see later, we use the same algorithm for the first order case, but storing BDDs in the nodes instead of the Booleans. The BDDs represent sets of assignments of the variables occurring free in the subformulas. The monitoring algorithm is here shown. It works on two arrays, pre and now, indexed by the numbers assigned to the subformulas. Initially, in step 1, all array entries in the now array are giving the value false. In step 2, we observe a new event. In step 3, we assign pre to become the now of the previous step. In step 4, we evaluate the subformulas. The purely Boolean subformulas have their obvious interpretation. Note that these only refer to the now array. The interpretation of the since formula is expressed exactly as the equation on the previous slide. Now phi since psi becomes now psi, or now phi and pre-phi since psi. That is, we look up the value of phi since psi in the pre-array. Similarly, with the previous phi formula, we look up the value of phi in the pre-array. In step 5, we go back to step 2. On this slide, we show how the formula just discussed can be translated into code, as explained in Havelund and Rousseau 2002. We declare the two arrays and evaluate a formula by evaluating the subformulas bottom up, from higher formula indexes to lower. We see specifically the assignment statements. Now of 2 is assigned pre of 3, going back in the pre-array. And now of 0 is assigned now of 1 and now of 2, just referring to the now array. We have now presented an algorithm for propositional past-time logic. With this, we can monitor properties like the one shown. When a close is observed, we should have seen an open in the past. Suppose we refer to the opening and closing of files. Such a formula can only refer to one file. One could, of course, for each file of interest, introduce open and close events and write a corresponding number of properties. However, This is not only laborsome, but also impossible since file names cannot be predicted. The solution is to introduce a first-order logic allowing predicates over data and quantification over such. Here we express the more general property that for all files F, if we observe a close of file F, then we must have seen an open of F in the past. We shall now introduce the pastime first-order temporal logic. The challenge is to monitor events that carry data, such as integers, floating point numbers, strings, etc. That is, not just Boolean propositions. Part of the challenge is to store such values efficiently for later reference.
As in the propositional case, we will restrict ourselves to past properties. We are going to look at first order or quantified pastime temporal logic, which we call here QTL. The syntax is extended as follows from the propositional case. Instead of propositions, we now allow predicates over variables and constants. We furthermore add existential quantification over variables. Amongst the derived forms, we have the previously defined ones for the propositional case. In addition, we add universal quantification. We also add an interval operator as a shorthand for slightly more complex since formula, used in the example in the box to the right. The example says that for every user and every file, if the user accesses the file, then the user hasn't logged out since he has logged in, and hasn't closed the file since he has opened it. A standard semantics for first-order temporal logic defines recursively when a subformula holds for a given triple consisting of an assignment for the free variables in the subformulas, a sequence, in our case this is the sequence of events, and a position in the sequence. The kind of bookkeeping that is needed to evaluate the formula requires keeping sets of tuples or assignments. We don't get any clue from standard semantics how to do that. We turn the semantics upside down and define a function that returns all the assignments for the free variables of a subformula that are satisfied for a given position in the sequence of trace. There are 2 points to note here. One is that when we need to complement or negate a formula, then complementation is done with respect to possibly an infinite set of assignments. We'll have to take care of that later with respect to BDDs. The second point is that the semantics definition is recursive in the structure of the formula. So in order to calculate the assignments that satisfy phi since psi in the current state, we need to calculate the set of assignments satisfying phi and the set of assignments satisfying psi. But according to the formula, we also need to calculate the set of assignments that satisfy phi since psi in the previous state, similar to the way we did phi since psi in the propositional algorithm. We will present now the main data structure for our algorithm, reduced order binary decision diagrams, ROBDDs, or simply BDDs. BDDs is a data structure for the compact representation of Boolean function. So the main goal is to represent a Boolean function with a small amount of memory. But in addition, BDDs are equipped with a bunch of procedures that allow us to process and combine BDDs. A BDD is formed from a binary tree that represents a Boolean function. The non-leaf nodes contain Boolean variables appearing in the same order along each path from the root to a leaf. The leaves contain a Boolean value either 0 for false or 1 for true. Following a path and assigning to a variable 0 if we exit it with the red dashed line, and a 1 if we exit it with the blue full line, the function returns the truth value that appears in the leaf. Now the tree is compacted into a directed acyclic graph, DAG, by combining isomorphic subtrees according to the rules in the next 3 slides. We can combine all the leaves with the same values. So we need at most 2 leaves, 0 and 1. If the left and the right successors of a node are the same, then the value of the formula does not depend on the value of the variable in that node. So we can remove it and redirect its incoming edges to point to its successors. According to the third and last rule, if we have nodes with the same left successors and with the same right successors, then we can combine them. We cannot apply here any further reduction rule, so we're done. We have a reduced form, and notice that the reduced form is unique, regardless of the order of applying the reduction rules. Different variable orderings change significantly the BDDs. In this example, there's a function such that according to one ordering, in which the variables appear in ascending order, x1, x2, until xn, the growth, depending on n, is linear. On the other hand, if first the variables that are odd appear, and then the variables that are even, then the BDD grows exponentially with n. In addition to compactness, the BDDs are equipped with procedures to combine and transform them. The first operator we'll see is the restrict operator. It replaces a variable by a constant, 0 or 1. Restricting x to 0 is done by redirecting the incoming edges of a node that is labeled by the variable x to its low successor, and then removing that node. And similarly, for restricting x to 1, its incoming edges are redirected to its high successor, and then x is removed. Then we may need to reduce the BDD. Let's see now how to apply a Boolean operator on 2 BDDs. So f and g are 2 Boolean functions that are represented using BDDs, and we want to combine them using a Boolean operator, which we denote by hashtag. And hashtag can stand for AND, OR, XOR, or any binary Boolean operator. Calculating f hashtag g starts at the root of the 2 BDDs for f and for g, and works its way down the directed acyclic graph to the left and to the right recursively. Applying the operator hashtag to the leaves simply calculates the Boolean function on their values. The naive application of the recursive procedure may result in that the same subgraphs are calculated again and again. Therefore, we use a dynamic programming principle called memoizing, where each time that we calculate the function with 2 parameters, we keep the result of that calculation, and next time that we reach a call with the same parameters, we do not calculate again, but use the old result. This allows us to reduce the complexity of applying a Boolean operator on 2 BDDs into twice the multiplication of their sizes. Now, as in all the operators that we presented so far, after completion of the procedure, the BDD may not be reduced, and we need to apply the reduce operation. BDDs represent Boolean functions, and Boolean functions can be expressed using propositional logic. In propositional logic, adding existential or universal quantification over Boolean variables does not change the expressive power. However, sometimes it's useful, for example, to present some Boolean function in a more compact form. Given a BDD that represents the Boolean function phi, we can easily generate a BDD that represents exists x phi. We do that as follows. We first take the restriction of phi where x is restricted to 0. Then we take the restriction of phi where x is restricted to 1. And then we apply the disjunction on these two BDDs. We want now to represent sets of assignments to variables, in this case of type integer, as BDDs. In this example, we want to represent two assignments. The first one, x is 0 and y is 0. And in the second one, x is 1 and y is 1. In each assignment, we represent each value of a variable as a bit vector with 3 bits. And then we can concatenate these vectors. Here's a BDD that corresponds to the first assignment. It returns 1 exactly when all the bits are 0. And here's a BDD that returns true or 1 exactly for the assignment 001, 001. The BDD in this slide returns 1 or true if the assignment is either the first one or the second one presented in the previous two slides. We will present now an algorithm for runtime verification for full first-order past-time linear temporal logic. The first system that allows runtime verification of past first-order temporal logic is by basing it out. This system, called Monopoly, is based on database operations and is limited in the way it handles negation of subformulas. We are going to describe here the theory and algorithms behind the system Déjà Vu developed by us. The algorithm and implementation are based on BDDs. The set of assignments is represented as a BDD. Then taking the union between sets of assignments can be implemented by taking the disjunction between BDDs. And taking the intersection between sets of assignments can be implemented by taking the conjunction. Complementation is implemented by taking the negation, and this is very cheap because all you need to do is swap in the BDD the leaves with 0 and 1, or false and true. Here's a very important trick. We're not going to keep the values directly in the BDD. We're going to enumerate the values as we see them. Each time we see a new value in an event, then we check whether it appeared before. If not, we hash it and give it a new enumeration value. Using successive enumerations would help the BDD to compact well. So if we see 4 events with values tel, dict, out, and tel2, then we successively enumerate them as 0, 1, 2, and 3, and convert these values into bit vectors. Here we see 4 BDDs, each one representing one of the 4 bit vectors. And we can combine them into one BDD that represents all 4 of them. Now, how many bits do we need for the BDD? Well, with n bits, we can have 2 to the power of n enumerations, or 2 to the power of n values. And note that the BDD represents assignments, and it needs a separate number of bits per each variable of the assignment. Now, we can start with some value of n, hoping that it would be sufficient. And then if we need more bits, then we can on the fly increase the number of bits. Here is an important ingredient of our representation that allows us to monitor properties without restricting the negation of subproperties. At any point of the monitoring, we have seen only a finite number of values, and we make sure that we have enough space to represent more values. In particular, at least one value is not used. We keep for that the highest enumeration, 1, 1, 1, 1, 1. Now, any enumeration that has not been used so far corresponds to the values that were not seen so far. Well, this is simple, and now negation is unconstrained. In the propositional runtime verification case, we kept a summary of the traced monitor so far that consisted of 2 bits per each subformula. For subformula phi, pre-phi was 1 exactly when phi held in the current trace excluding the current event, and now phi was 1 when phi holds in the current trace. In the first order case, for its subformula, we keep in pre and in now BDDs instead of Boolean variables. Each BDD represents assignments to the 3 variables that satisfy the formula. In pre, if it satisfies that formula in the trace excluding the current event. In now, if it satisfies it now in the current trace. So for the subformula phi since psi, we need BDDs for phi since psi, for phi, and for psi. Seeing a new event extending the trace, we need to update the pre and now BDDs. The principle is very similar to the way it is done for the propositional case. So for example, if the subformula is phi since psi, then now of phi since psi is set to now of psi, or both now of phi and pre of phi since psi. This is the same update as in the propositional case. However, now the and the or are conjunction and disjunction between BDDs. This is the algorithm for the first order monitoring. It is very similar to the propositional algorithm, but it utilizes the operators between BDDs. There are several cases that require special treatment in the first order version of the algorithm. When it appears, if it contains a new value, then a new enumeration is generated and is hashed for that value. So the further appearances of that value will use the same enumeration. A BDD that represents this new assignment is generated. For a subformula of the form exists x phi, we apply the BDD exists operator for each bit in the bit vector for x on now phi to obtain now of exist x phi.
We will now have a look at the implementation of the runtime verification algorithm just presented in the Déjà-vu tool. The tool is available open source on GitHub. Déjà-vu is implemented in the Scala programming language. The tool here visualized as a small mechanical wheel in the middle takes a specification as input, shown in the upper left corner, and produces as output a Scala program shown to the right. The specification file can contain one or more properties. The specification parser is implemented using Scala's parser combinators. The generated Scala program takes as input a log file in CSV format and produces a report of violations. In the CSV format, each line represents an event, with the event name appearing first and then the arguments to the event occurring after, all separated by commas. Note that, as shown, this review is set up as a log analysis tool. The techniques, however, can be applied in online analysis as well, with some adjustments. The generated monitor uses the Java BDD package, which is a well-aged BDD package. Last update to this website was in 2007. The package is implemented in Java. Since Scala runs on the JVM, Scala can import and use such a library without any issues. The Java BDD package is built on top of the body BDD library written in C. There's also a mapping to the code library written in C. Here's the grammar for writing specifications. It is extracted from the implemented parser and is part of the user documentation. Note that the grammar shown here does not include various extensions to the logic that we shall briefly explain later. A specification document consists of a sequence of definitions. A definition can be an event definition defining its name and how many arguments it has. Events do not need to be declared, but if provided, provides an additional level of type checking. A definition can also be a macro definition. Macros with events are just a convenient way of naming subformulas. Finally, a definition can be a property definition having a name and a body, a first-order past-time temporal logic formula. The main takeaway is that the grammar is small and easy to learn. We shall now provide an example of a trace analysis using the implemented algorithm. We shall in this presentation see BDDs produced by the tool on the way. At the top, we see the formula we want the trace to satisfy. It states that for all files if there exists a datum D that is written to the file F, then in the past the file F must have been opened and not closed since. We shall use just 2 bits for representing enumerations of values observed in the trace for each of the variables F and D shown in the blue box. Since the enumeration 11 is reserved for representing all data not yet seen in the trace, we are left with 3 enumerations for each variable, namely the bit patterns 00, 01, and 10. Note that I read the bit patterns from left to right. The trace we shall analyze is also shown, consisting of 9 events. As we shall discover, the 8th event causes us to run out of enumerations. We have a magic trick to deal with this situation, which we refer to as garbage collection. Let us launch into it. It is not important that you get all the details, but at least you may be able to see the patterns. This review is called as shown on this slide. It takes as arguments a specification file, a log file, and then some additional arguments. One of these arguments is the number of bits to be used to represent the enumerations for each variable. In this case, we use 2 bits as explained on the previous slide. To the left, we see the abstract syntax tree for the formula. It shows how the formula is broken up into its subformulas, and it shows how these subformulas are numbered from 0 to 7. To the right, we see a small part of the Scala code generated for this property. It specifically concerns the evaluate function, which is called for each new event. It shows how each entry in the now array is updated, starting with the highest index 7 and moving down to 0. After the now array has been computed, we determine whether an error has occurred, which is the case if now of 0 is a 0 BDD, yielding false for all enumerations. We return true if and only if error is false. We also see how the pre-array assumes the value of the now array for the next step. If we look closer at the assignments to the now array, entries 7, 6, and 3 get their values directly from the events observed in the trace. This is the lookup function referred to earlier. For example, now of 7 pattern matches against an open in the trace with a formal argument if. Entries 5 and 1 are just applications of standard Boolean operators. For example, now of 5 is a negation of now of 6. Entries 2 and 0 apply existential and universal quantification over variables. Finally, entry 4 refers to the previous value of node 4. That is, now of 4 is either now of 7 or 5 and pre of 4. Here the log is shown in CSV format. Also shown is the abstract syntax tree. The formula contains two variables f and d. For each, we use 2 bits to represent their enumerations. Since 1, is reserved to represent values not yet seen, we have available the bit patterns 0, 0, 0, 1, and 1, 0. We name the bits representing the file name f as B0 and B1. Here, B0 is the least significant rightmost bit, and B1 is the most significant leftmost bit. The BDD shown represents all the enumerations initially available for the variable f, or free as we shall call it. This BDD represents the bit patterns 0, 0, 0, 1, and 1, 0. The only bit pattern not included is the reserved bit pattern 1, 1. This is shown in the BDD by the fact that the only path leading to 0, which is false, is the path B0 is 1 and B1 is 1. All other bit patterns lead to 1, which is true. Note that when I refer to a bit pattern, I read it from left to right, as in 0, 1, representing the natural number 1, mentioning the most significant bit B1 first and the least significant bit B0 last. This is how one normally speaks binary numbers. However, when I refer to a path in the BDD, I refer to the least significant bit B0 first, reading from the top of the BDD, since this is how the BDDs are laid out. For example, take the bit pattern 0, 1, which is free. Here B1 is 0 and B0 is 1. If we follow B0 is 1 and B1 is 0 in the BDD, we end up in the 1 leaf. This means that this bit pattern is free for use. The fact that we use a BDD to represent the free enumerations allows us to use a SAT solver to choose a free enumeration that satisfies the BDD. Although we shall not go into the details, this approach also later allows us to perform garbage collection. Now we observe the first event open of F1. The enumeration chosen to represent F1 is 1, 0, the natural number 2, chosen by the SAT solver applied to the BDD of free enumerations. The BDD shown represents this enumeration, here reading from the top from least significant bit B0 to most significant bit B1. The path B0 is 0 and B1 is 1 leads to true, and all other bit patterns lead to false. This is the BDD stored in the now array in position 7, corresponding to the open F predicate. The BDD stored in position 4 of the now array represents the subformula not close of F since open of F. That is, all the files that have been opened until now and not yet closed. In our case, only the file F1 has so far been opened, represented by the binary number 1, 0. In the BDD, we read this bit pattern from right to left by starting at the top of the BDD. The path 0, 1 leads to true. This is exactly the same BDD as before. We can now evaluate the other subformulas. Now of 3, representing the right predicate, obviously evaluates to false. Consequently, the existential quantification above also evaluates to false. The implication in position 1 now evaluates to true, since the left argument to the implication evaluates to false. Consequently, the whole formula evaluates to true, as we would expect. We can now look at the available bits left. Since we used the pattern 1, 0, we are left with 0, 0 and 0, 1. That is, the leftmost bit is 0 and the rightmost bit can either be 0 or 1. The BDD shows these available bit patterns. All bit patterns where B1, the most significant bit, is 0 lead to true. Note that the BDD does not refer to B0, the least significant bit. This is because it can be either 0 or 1. We now observe the second event, open of F2. Here we assign the free bit pattern 0, 1 to represent F2. The BDD represents this bit pattern in that B0 equal 1 equals 0 leads to true and all other bit patterns lead to false. Node 4, representing the subformula not close of F since open of F, is now more interesting. It now denotes the BDD of enumerations representing the two open files F1 and F2. These enumerations are 1, 0 for F1 and 0, 1 for F2. We can see in the BDD that these are exactly the bit patterns leading to true. Take the bit pattern 1, 0 for F1. We follow the path B0 equals 0 and B1 equal 1, which leads to true. Likewise, the bit pattern 0, 1 for F2. We follow the path B0 equal 1 and B1 equals 0, which also leads to true. We can now evaluate the rest of the subformulas, which evaluate as we would expect, since there's no right event observed in the trace. As we can see, the whole formula evaluates to true, effectively because we have not yet seen a right event. Note that it is only upon a right event that we can potentially detect a violation. Here we observe the third event open of F3. The last available bit pattern 0, 0 is assigned to represent F3, shown in the BDD where only 0, 0 leads to true. Now node 4, representing the subformula not close of F since open of F, represents all bit patterns used, which are all patterns except the reserved pattern 1, 1. 1, 1 is therefore the only bit pattern leading to false in the BDD. Now we observe the closing of file F1. Node 4, representing the since formula, now denotes the enumerations for the remaining open files F2 and F3. These are the patterns 0, 1 and 0, 0. That is, the leftmost bit is 0. In the BDD, this is shown by B1 leads to true. Again, B0 is not shown since its value does not matter. After closing all the files, node 4, representing the since formula, now denotes false. By the way, the set of 3 enumerations is also false, since we have not updated it. Now we observe the opening of file F1 again. We already in the past assigned an enumeration for F1 in the 1, 0, and we can reuse it. The BDD represents this bit pattern. In node 4, representing the since formula, the enumeration 1, 0, representing F1, is now the only open file, shown by the BDD. Now we observe open of F4. At this point, we have run out of enumerations. The BDD denoting free enumerations is false. Our framework allows us to perform garbage collection, identifying which enumerations are no longer needed and therefore can be reused, creating a new BDD of available enumerations for the variable f. We shall not go into the details of how this is done. The paper mentioned at the bottom of the slide explains the approach. Recall that enumeration 1, 0 was already reused to represent the reopened file F1. The remaining available enumerations are therefore 0, 1 and 0, 0, which are all enumerations where the most significant bit B1 is 0. This is shown in the resulting BDD of available free enumerations for the variable f that only refers to B1. B1 being 0 leads to the true leaf node. Now the SAT solver yields the pattern 0, 1 for the open file F1. Finally, we encounter a write event with the arguments F4 and 2, matching the predicate write f, d in the formula. We used bits B0 and B1 to represent files f, and we now use bits B2 and B3 to represent the data d. F4 is represented by the enumeration 0, 1 from before, and the data 2 is represented by the enumeration 1, 0. The BDD shows the concatenation of these two patterns. This is the BDD stored in node 3, representing the right predicates. In node 2, we perform existential quantification over D, removing bits B2 and B3, resulting in a BDD referring only to bits B0 and B1, representing the file F and denoting the enumeration 01, which represents the file F4. We will next look into an extension of the logic with time. This will allow us to monitor whether events occur within or beyond given time bounds. The challenge is to store time within the same BDDs that we use to represent data values. Note that while the enumerations representing data values only are compared with equality, time values have to be compared with inequalities, and we need to perform arithmetic operations on them. They therefore differ from our previous enumerations. As an example of what we want to support is the following property. It states that a success of a command should be preceded by a dispatch of a command within 4 time units in the past, and no fail of the command occurring since then. We see that we annotate the since operator with a time constraint. We obtain the syntax for the extended logic by adding 2 new subformulas, both variants of the since formula, but with added time constraints. The first one states that the right-hand formula of the since operator should be true in the past within the given time bound, small delta. The second formula states that the right-hand formula of the since operator should be true in the past at some point beyond the time bound, small delta. Otherwise, the semantics of these operators are as the on-time version. We can also derive new time versions of the operators past and history with their obvious meaning. For example, sometime in the past within delta time units, phi must hold, and sometime in the past beyond delta time units, phi must hold. Likewise, always in the past within delta time units, phi must hold, and always in the past beyond delta time units, phi must hold. We now consider a trace as consisting of a sequence of binary tuples, where the first element is the event itself, the element is the timestamp. The semantics of the 2 new formulas is as shown below. We shall just explain the first formula. The second follows obviously from this definition. The formula holds in position I if there is a past position j such that the time difference between the 2 positions is less than or equal to delta, and psi holds in position j and phi holds in all positions k since then. In the extended algorithm, we now need to incorporate the time values as part of the bit patterns stored in BDDs. Whereas before, for variables x1 to xn, we stored the enumeration in concatenated form, we now add an extra sequence of bits, t1 to tn. This time value is the binary representation of the actual time that has passed since the data represented by the other enumerations were observed. Said more succinctly, each enumeration representing a piece of data is associated with the time passed since the data was observed. Let us look at our example property from before, that a success of a command is preceded by a dispatch of the command within 4 time units in the past, and no fail in between. Here is shown the abstract syntax tree of the formula. We shall specifically focus on the subformula 4, namely the since formula. Consider the following log. Each event in the log has as last argument a timestamp. So the first event occurs at time 10, the second at time 12, and the third at time 13, etc. In the first dispatch event, we represent the command value stop by the 3-bit enumeration 110. In the second dispatch event, we represent the command value off with the enumeration 101. In the third telemetry event, we note that the time since the first dispatch event is 3, and the time since the second dispatch event is 1. Note that we used 3 bits for representing data. We use 4 bits for representing time. The BDD to the right is the BDD denoted by the since formula at the third telemetry event. It shows that the command stop, represented by the bit pattern 110, was seen 3 time units ago, and the command off, represented by the bit pattern 101, was seen 1 time unit ago. To see this, take the enumeration 110, representing the stop value observed in the first dispatch event 3 time units ago. The time value 3 is represented by the bit pattern 0011. Reading these values from right to left, moving down the BDD from the top, we get exactly that. 0, 1, 1, 1, 1, 0, 0 leads to true. The time value occurs at the bottom of the BDD. In the previous example, we set aside 4 bits to represent time. How many bits do we really need to represent time for a formula containing a time constraint delta? We claim we need 2 times delta plus 1 bits. To see this, observe the following. We do not need to store time values bigger than small delta plus 1. However, during monitoring, we may have to compute values going beyond this bound, but not bigger than 2 times delta plus 1. The argument is outlined on this slide, and you can go back to the slide later and follow the argument. So how does the algorithm work for handling time? First of all, think of a BDD as representing a relation R consisting of a set of pairs, where the first element of a pair is an enumeration representing some value observed in the trace, and the second argument is the time t since the value was observed. These enumerations and time values are in reality bit vectors. Abstractly, we now need to create 2 functions, one that adds a time delta to all the time values of a relation, and one that filters all pairs where the time value is bigger than some time delta. These functions are shown here in the red box. The first function adds a time delta to all the time values in the relation R. This is shown abstractly in the first line of the first bullet. This can be done by first constructing a relation T consisting of all pairs of time values T, T prime, where T prime is T plus delta, and then taking the join of R in that relation. Then projecting out the old T values and rename the new T prime values to T. The second function filters all pairs x, t in the relation R, where t is bigger than some time value delta. This is shown abstractly in the first line of the second bullet. This can be done by first constructing a set t delta consisting of all the time values t that are bigger than delta, and then taking the join of the relation R and that set. On the next slide, we shall construct the relation t and the set t delta, where we name them respectively addConst and GTConst. The 2 BDD creating functions mentioned on the previous slide are shown here. They look sophisticated but are not really complicated. The implementation follows these formulas very closely. The first, addConst t, t prime, big delta, represents all enumerations t, t prime, and big delta, where t prime is the sum of t and big delta. The definition is a classical addition algorithm using carryover bits R. The second function, greater than const t, small delta, represents all enumerations t and small delta where t is bigger than small delta. This is done by comparing the from most significant to lower significance and terminating with a result when bits differ. We can now define the algorithm for the formula phi since psi in less than or equal to delta time units. Again, the formula looks a bit compressed and it takes some time to comprehend it, but effectively it states the following. We introduce 2 new arrays, t-now and t-pre, which denote BDDs that include the time constraints. The now and pre arrays from before do not include the time values. T-now of the formula is defined as follows. Either psi holds now and we reset the time of t to 0. Or psi does not hold now, but phi does. And the previous t value is determined by t-pre of the sense formula, to which we add delta giving t prime, which must not be greater than small delta. Then t is removed by quantifying over it and t prime renamed to t. The BDD for now of the sense formula is obtained from t now of the formula by projecting out the timer value. The algorithm for the sense formula, including a bigger than delta constraint, is a bit more complicated. It uses a predicate equal t, c, which represents all t and c enumerations that are equal, strangely enough modeled by stating that t is 0 added to c. We shall not explain the algorithm further here, but the audience can study the formula in the paper. We performed an evaluation of déjà vu's handling of time constraints By verifying variance of the properties shown on the left on a set of traces of different length and structure, each property was verified with and without time constraints on one or more traces numbered 1 to 15. The factor of slowdown for verifying with time constraints compared to verification without time constraints is shown in the rightmost column. It is clear that there is a cost to monitoring time properties compared to monitoring on-time properties. Furthermore, the larger the time constraints, the more calculations the monitor has to perform on bit strings representing time values. The performance of déjà vu is acceptable for time constraints that require no more than 7 bits of storage. We observed, however, that going beyond 7 bits causes the monitor execution to become considerably slower. In conclusion, we presented a pastime first-order temporal logic with timing constraints, with no limitation on the occurrence of quantifiers. Data and time are represented in BDDs. The handling of time, including addition and comparison, suggests a general approach for handling operations on integers. However, bit vector operations using a BDD package has efficiency issues. Future research will investigate this issue. Thanks for listening to this talk.
Thank you, Klaus, and thank you, Doron.
Yeah, let me try to stop sharing.
All right, thanks for the great talk. So we have time for a few questions. If you have a question, please raise your hand. There is a raise hand function at the bottom of your screen. All right, I see the raised hand by Dmitry. Please unmute yourself and.
Yes, hi. Thanks for the talk. I do wonder, so I have two questions actually, and the first one is about the statement about unrestricted quantifiers. So if you have only one special value and you have equalities in your formulas, then I guess you cannot do this with just one special value. So I would imagine that you restrict the quantifiers in this case. Is this correct?
This is true. This is Doron. I'm the other voice in the. This is correct. You should not have a non-equal. Yes.
So do you have some ideas about getting rid of this limitation?
Yeah, but it would complicate things. So since this did not appear much in the formula, I mean, you know, in first order logic, when you don't have the equal sign in first order logic, always you have the equal sign as a defined relation, right? It's built in. It's not part of the relation, and that's exactly the reason. So if you don't have the equal, you cannot even say how many elements you have, right? And here it's the same. It makes things simpler. It costs you, and it's a very good comment. We should think if we want to, but then obviously we need to have more than one element for all the values we haven't seen, right? Mm-hmm. And at the moment we have this 1, 1, 1, 1, and it works like a charm, right? We don't even have to do anything just to keep place for that. And
as long as you don't have a column.
Exactly.
Oh. Yes. Yeah. Thanks. So my second question is about time. So it's quite interesting the way how you encode time in BDDs, but do you have an idea how this compares to other approaches for handling time, namely using some queue-like sliding window data structure?
In a sense, there is a sliding window here because we keep the delta, okay? Yeah. But I mean, I think the main trick here is that we encode the time as small integers and then generate bit vectors. And then we can apply binary operators on bit vectors, okay? And that's pretty quickly and efficient. On the other hand, if the distances in the intervals are too big, then in fact we have a considerable degrading of the performance. and then maybe we could use the other methods. But since our method is based on BDDs, where intersection is and union is an or, etc., and we get that all very, very fast, then that is combined well. And of course, as in the previous question, if you want to go out of the restriction of very small intervals, then we have to pay for it greatly, and the performance probably would be degraded enormously.
Thanks. I was just thinking that you don't have to give up BDDs, right? You can combine your BDD approach with the queue-based approach for handling time.
It would be very complicated to do, and the reason, I mean, there was no time to. There are some slides which we removed, which show you what kind of bookkeeping you need to do, and you need to keep the time distance per data value. So you need to keep a lot of time distances. There's a set of time distances, and if it's a big set of big time distances, then handling in a different way, probably with the queue or sequentially, would degrade the performance. I mean, this system is so extremely fast because the BDD kind of does it all in one fell swoop. We don't calculate things. We don't update the intervals, for one time step at a time, for one element at a time. We do it all in one fell swoop. Once we have a time interval, boom, all the values are updated using these BDD encodings. I mean, it's not working sequentially. What you're saying would cause it to work sequentially, and that would not be so good here. I mean, we would be able to do something, we would be able to expand, but the performance would be degraded. If you know a magic where this would not happen, please let us know.
I would be just interested to evaluate the two. I don't think it's such black and white that one scheme is superior in all cases to the other. Thanks.
All right, thanks for your question. Are there any other questions? Please raise your hand. While hands are being raised, let me ask a question about monitoring so the examples you gave in the talk were all of the closed formulas with the quantifier at the top for all variables. So what changes when you have free variables in the formula? So looks like your BDD encoding certainly would be able to handle that, but something definitely would have to change at the top level of the algorithm, right? And the garbage collection may not work, right?
No, nothing would be changed. I mean, the only thing is that if we have, I mean, the sub-formulas have free variables, right? So if the entire formula has free variables, that could have been okay, but we assume that in runtime verification, you want an answer of yes or no. So if the answer is the sub-formula, if the formula itself that you check has still free variables, then what would you report? You report sets or tuples of numbers, right? And that would be too much information. But the algorithm would work exactly the same with everything, the garbage collection, which we didn't talk about the garbage collection here, but we do have, everything would work at the same. It's only the issue of what kind of response you want. And we assume you want a response yes or no. And therefore we...
No, wait, so sorry to interrupt. So given your example with open and close files, I want to see where the violations have occurred. And so I want to know that on F3, is the problematic file, yes, right? And so that would be a Boolean true among zeros, right? But this means I cannot garbage collect the ones that are essentially closed, right? Or I somehow have to maybe only garbage collect the ones that are closed and without raising violation or something like that.
First of all, it's very, sorry.
I can say that the Mon-Poly tool operates with the notion of open formulas, right, where variables are free. And you get as information not only true and false, but also which values violate a formula or satisfies a formula. So yeah, we don't do that.
We could have set it up, at the same cost, we could have set it up to do that. It's interesting that you mentioned the garbage collection. So you must know this system from another lecture because we didn't talk about it, which is, is very nice. But the garbage collection would work very well because what the garbage collection does, in fact, is, basically the garbage collection allows you to reuse enumerations. And the enumerations that you garbage collect are those which would not affect the formula in the future. So if these values are in the output, if you set out the output to allow these values, as you suggest, which is possible, then it would not garbage collect it automatically, because what it does is automatically checks which values behave in the same way as values which haven't been seen before. So if that value is in the output, certainly does not behave as a value that has not been seen. So the answer is no, it would not. There will be no change whatsoever. It's just kind of the interface. We need to change the interface and it will do that.
There is one problem that since we work with BDDs, so we have this hash map. When you see a value in a trace, you map the value to an enumeration, which then becomes a BDD. So what you have when you evaluate a formula, you get a set of bit patterns as the result of the formula. And you will then have to go backwards in this hash map and get back to the values for it to make sense for the user, right? So that is a problem that would have to be solved.
All right. Thanks for your explanation. It makes sense. Are there any other questions? I don't see any other raised hands. If I missed your raised hand, please speak up. And if not, then let us all thank Klaus and Doron for a very nice talk. I, for myself, learned a lot, so thank you very much.